All right, so 9-1, we're going to start talking about sequences. And we're going to do kind of a general overview today. So if I go too fast, just stop me. I'm kind of assuming that you've seen a lot of this and it's a refresher. Because there's a lot of notes to go through, aren't there? Yeah. So the first thing that we're going to do, we're going to talk about a sequence in general. First of all, a sequence in general is just a list of numbers, right? And it's generated by the position that that number's in. So there's the first number, the second number, the third number, the fourth number. And each of those numbers, if I'm talking about the first number, we use its position as part of the pattern in its sequence. And so you have to pay attention to what position it's in and what its value is. That's because you're going to have to create equations today for these sequences. So some are harder than others. And then infinite sequence just means it continues forever. It never ends. Whereas a finite sequence, there's a definite beginning and a definite ending. So there might be 10 items in a sequence. Whereas an infinite, I can't count them. I can see. Apparently not. All right. So we're going to find the nth term of a sequence. You might be asked to find the 50th term or the first 10 terms or something like that. So pay attention to your directions. You might have an arithmetic sequence or you might have a geometric sequence. It depends. And you should have explored those in algebra. Did you or did you not? And definitely in Algebra 3-4 last year, right? Thank you. All right, so it's not asking you to determine whether it's geometric or arithmetic. You just are finding the first 4 terms in the sequence. So I'd like to see the following work. I don't want to see it in your head, fortunately. So we're going to find a sub 1. So a sub 1 just means I'm finding the first term in the sequence, and the n in this pattern refers to that position in the sequence. So I've got 3 times 1 minus 2, which is what? What value does that give you? 1. So the first term of the sequence is 1. Then a sub 2. Running through that pattern, bless you. So this time we have 3 times 2, which is 6, minus 2 gives us 4. So 4 is the second term of the sequence. A sub 3. Pardon? Yep. I want to see this work. Putting 3 in, so 3 times 3 is 9, minus 2 is 7. And by the third term of the sequence, you should start to see a pattern of some sort, typically. What's happening here? Yeah, we're increasing by 3, and notice that what's in front of n is 3. This is going to help you figure out the patterns later when they don't give you the sequence pattern. And so the next one we anticipate is going to be what? 10, right? So a sub 4 is equal to 3 times 4, which is 12, minus 2, which is indeed 10. Then I will suggest that you take your calculator and check your pattern on your calculator to see if you're correct. We're going to take our handy-dandy calculator. And I'm going to go into y equals, clear out anything that might be there. Thank you. And we're going to plug in this sequence here, 3x for our purposes, minus 2. And then if I go to tables, I want my table, so go to second function calc, or I'm sorry, second function graph. And I can just input 1, 2, 3, and 4. Are those the values that I just got? Now, if you're not able to input it, go to your table set, which would be second window, and your independent needs to show ask. Your dependent needs to show auto. And then auto allow you to put it in there. Okay, so that's just a quick check for you. All right, so then look at the second sequence. You run it through the second sequence. This time, your n is an exponent. And you need to get in the habit of doing a sub 1, painful though it is, equals. So that one, is that arithmetic? Is it? No. Is it geometric? Do you remember what geometric is? Arithmetic means there's a common difference. So although there's a common difference here, it's going up by 2 and then down by 2. So it's really not a common difference. It's a plus 2 and a minus 2. So it's not arithmetic. Geometric means you multiply or divide by the same number. Multiply by 2, divide by 2, multiply by 2, so it's not geometric either. But there's definitely a pattern, isn't there? Okay. And again, if I were to put it on my calculator, we check it. So go into y equals, figure that out, and put in 3 plus, use parentheses, -1, raised to the x. And go to second graph for your table. And you get 2, 4, 2, 4, 2, 4. Don't worry about the errors that are showing on mine. Okay, so it does check. All right, so then look at finding the nth term of a sequence. So we actually have to come up with the pattern or something. So if you're familiar with arithmetic sequences, we'll get more involved with those later this week. I'll give you a definite way that you can find those once you identify that it's arithmetic. So the first one here is arithmetic, isn't it? How do I know that this is arithmetic? Yeah, it's increasing by 2. So remember, with this one up here that was arithmetic and it was increasing by 3, what did we notice about what was in front of n? Yeah, there was that 3 in front. So don't I anticipate that I should have 2n here? If my common difference here is always 2, plus 2, plus 2, plus 2, I might think, because remember n is the position that that thing is in the sequence. So I'm going to set up a little chart here. So n versus whatever we come up with. So I've got the first term, the second term, the third term, and the fourth term. Hopefully by the fourth term we'll start to see a proper pattern. So if I have n, then my a sub n turns out to be 1, 3, 5, and 7. That's the pattern that they gave me, right? Well, the difference between these two is nothing. 1, 2, 3. Right? We know that the common difference is always 2. So can't we start off with saying, okay, what if I had 2n? What would I get? So here's n. 2 times 1 is 2, right? 2 times 2 is 4. 2 times 3 is 6. And 2 times 4 is 8. How far apart are we now? 1, 1, 1, 1. How do I go from 1 to 2? Do I increase it or decrease it? Increase. So if I add 1 each time, will that work? So then perhaps my pattern's not 2n, it's 2n plus 1. Does that work? So if I add 1 to each of these, now I get, oops, I want to add 1 to this one. That didn't work, did it? So what should I have done? I really want to go from here to here, don't I? So I want to subtract 1. So you can fix it pretty quickly, right? Just by looking at the first one. So if I take 2n and I subtract 1, I'll get 1. Subtract 1 here, I get 3. Subtract 1 here, I get 5. And then 7. Now does it seem to work? So then your final answer would be written this way. So a sub n is equal to 2n minus 1. That will get you your nth term. So now if I wanted to find the 1,000th term, I could plug in 1,000th being the 1,000th position in the sequence. Plug in 1,000 here, I get 2,000 minus 1, which is 1,999. Right? All right, so that one was a little easier. Let's look at this one. We're just doing a little guessing and checking. Move that up a little bit. All right, so we have n. We've got 1, 2, 3, 4 terms. So 1, 2, 3, and 4. And then we have a sub n. We've got 2, 5, 10, and 17. Do you see a pattern here at all? Increase by 3, 5, 7. 3, 5, 7. That's kind of a pattern, isn't it? Say that again?
All the odd numbers.
You're adding by odd numbers, right? Okay. So, to go from here to here, I could multiply by 2, right? But that's not going to help here. So 2 times 1 is 2. That gets us there. But 2, so if we just look at 2n, see if that helps you at all. 2n is going to give us 2, 4, 6, and 8. Anything at all? Did that help at all? If it's not arithmetic, that's probably not going to help. What else might we try? Squaring it. So what if we had n squared? So if we squared this, we get 1. Still doesn't get us to 2, but let's look to see what we get. 2 squared, which is 4. 3 squared, which is 9. And 4 squared, which is 16. We're a lot closer, aren't we? 17 and 16 is 1 off, 10 and 9 is 1 off, 5 and 4 is 1 off, and 2 and 1 is 1 off, right? So how do I go from n squared back to where I want to be? Plus 1, plus 1, plus 1, plus 1, right? So if we had n squared plus 1, then all we'd end up with is this plus 1 is, make my chart, and I don't want this one now, so I'm going to cross that one out. So if I add 1 here, I get 2, 3, 10, and 17, which is what I want, correct? Oh, 5, not 3. Sorry. Which is what I want. So then a sub n is equal to n squared plus 1. So sometimes you might have to square or cube something to try to figure out the pattern. Then look at C. C is a little different. You've got 2 fractions and a non-fraction, right? If you've got fractions and one is not a fraction, if I were you, the first thing I would do would be to put 2 over 1. Make them all a fraction. Do you see a pattern forming? 2, 3, 4, 1, 2, 3, right? So remember we've got n. 1, 2, and 3, because I only have 3 terms in my sequence. And then a sub n, I'm going to write it as 2 over 1, 3 over 2, and 4 over 3. So let's just work with the numerator for right now. How do I go from n to what we have in the numerator? Is there always the same difference? If n is 1, how do I go from 1 to 2? Add 1. Does that work here? 2 plus 1 is 3. 3 plus 1 is 4. So could our numerator be n plus 1? Right? And our denominator, how do I go from keeping n again? Look at your denominator. What do you notice? It's n. So will that work? 1 plus 1 is 2 over 1. There it is. 2 plus 1 is 3 over 2. That works. And then 3 plus 1 is 4 over 3. It works. So then you're going to write your sequence as a sub n is equal to n plus 1 over n. So sometimes you have two different patterns going on at once. Yes? Could you do n minus 1 on the bottom? Let's just try it. And then put n on the top. Would you get the same thing? Is that what you're saying? So if I had 2, I would put 2 here over, I'm sorry, 1, because n is 1, right? So I'd have 1 over 0. So it's a thought, but it doesn't work, right? And all you have to do is play with it. It's a good thought. Any other thoughts? All right, so those kinds of questions you're going to just play around with today until I give you more structure to go along with it. So flip that. And that part might actually frustrate some of you. So just use some of those tools that we looked at. And if you do see a common difference, multiply that to n. And then add or subtract whatever comes into play. If it's not a common difference, start by squaring, cubing, or something like that. We're going to look at recursive sequences. So a recursive sequence just means that you always use 1 or 2 terms from the sequence to get another term. Oftentimes it's the previous term. So the Fibonacci sequence is one of the most common that you're going to see. This is well known. You've got 1, 1, 2, 3, 5, 8. What's happening in this sequence? Always add the previous first 2, right? So to get to the third term, I have to add the first and the second term together. For our purposes, we are going to let this position be the 0 position. Weird but true. So we're going to let a sub 0 equal 1. And we're going to let a sub 1 equal the next term, which is the second 1. And then a sub 2 is going to be the 2. If we come up with a sequence to describe this, recursive kind of looks at things differently. So think of it this way. If I wanted to find the second term, okay, so if I wanted to find a sub 2, didn't we take a sub 0 and add a sub 1 to it? Isn't that what we did? Let's break this into, they like to use k in your textbook for the sub number. I don't care if you use n or k, it doesn't matter to me. If you want to use n, that's fine. I'm going to break back into k because that's what your textbook does, and you're going to see it in your answers. So what if I said that this was a sub k instead of 2? Just a generic a sub k. How far back do I have to go from the second term to get to 0? How many terms backwards? 2. So wouldn't this be a sub k minus 2? This one right here? You see how I got that? Because I had to go 2 terms backwards to get to a sub 0. Then wouldn't I add to that a sub, how far back is the first term from the second term? 1 back. So I'd have to do k minus 1. So if k is 2, 2 minus 2 is 0, 2 minus 1 is 1. This is a recursive pattern that describes that sequence. And you always have to know what number you start with. So they have to tell you typically the first number you're going to be given and then the pattern from there on. So you're going to play around with that a little bit. I'm going to add on to this just a little bit. What if you had a sub 1 was 28? You could put up the what if. And the sequence was a sub k plus 1 is equal to a sub k minus 4. So the first term, because that's position 1, is 28. What's k plus 1 in relation to k? Is it the one after or the one before? It's the one after. It's the next term in the sequence, right? So this is a little different than the one that we did over here, where we used a minus. So sometimes you have a minus going on, which means you go backwards. And if you have a plus, you go forwards. So I'm looking for the next term in the sequence. So, whoops, that's an A. So A sub k plus 1 would be A sub 1 plus 1, right? Because k is 1, equals A sub 1 minus 4. Don't we know A sub 1? Isn't 1 plus 1 2? So to get the second term of the sequence, we're going to take the first term and subtract 4, or the previous term. Well, the previous term is 28 minus 4, which is 24. How do you find A sub 3? What's the term before A sub 3? Wouldn't it be A sub 2, which is 24, minus 4 equals 20? A sub 4, what do you put here? 20, the previous term, so 20 minus 4 is 16. So this is a simple recursive, but I'm always, with recursive, you're always using typically the previous term, and so you put a new one in each time. So this one went here, this one went there, then this one will go to the next one. And that's what the Fibonacci sequence did, but it used 2 previous terms. So you have a couple of questions in your book that relates to that, so you'll review that. And then these are fun. Factorials. What does a factorial mean? For 3 factorial, you'll take what you start with here, 3. You multiply it by 1 less each time. So then times 2 times 1, which in this case would be 6. So what this is showing you above, this is showing you the sequencing or the pattern for a factorial. You always take n, whatever this number is, multiply it by 1 less than it, 2 less than it, 3 less than it, 4, and so forth, right? And so in this case, we had 3 times 3 times 1. It's 0 factorial. It's actually not 0. You'd think it'd be 0 because of the patterning there. It's always 1. So you need to highlight that. Zero factorial, its value is 100% of the time 1. It's essentially saying take no. I'll show you why here in a minute when we do some division. Oh, was that Kayla? I couldn't tell if it was Kayla or Paris. You're essentially not writing down any numbers and multiplying them together is really what it's saying to do. It's not 0 times 0 minus 1 times, do you see what I'm saying? And they have to be positive numbers. Because when we do factorials, we stop at 1, don't we? We can't stop at 1 here because we went beyond that. We're already below 1. All right, so look at 10 factorial. Now, once we get to 10 factorial, this is really 10 times 9 times 8, 7, 6, 5, 4, 3, 2, 1, right? That's a big number. It's a lot of multiplying. Would you like to know how to do it on your calculator? Does anybody know where it is on your calculator? Say that again? Oh gosh, you guys are brilliant. Yes, so find your math button. And then go to PRB, which stands for what? Probability, and you see it there at number 4. So, but I have to have my 10 in there first, so sorry, let's backtrack. So put your 10 in, and then go back to your math, go back to probability, oops, I didn't mean to do that, and then hit 4 or scroll down. And now I have 10 factorial and hit enter. Rather than have to multiply all that out, we have a really, really, really large number. So I have 3 million, it's not terribly large. 3,628,800. Aren't you glad I didn't make you multiply that by hand? So there's a difference between D and E, by the way. What's the difference? Yeah, parentheses. So 2 times n factorial just means 2 times. And then you're going to have 1 times 2 times 3 times 4 times n, right? So I'm going backwards. That's really what that means to do. So that would actually be my answer. Versus this one. This one, my final, just like on this one here, the 2 was not being taken into account in the factorial, but my ending number was n, right? So if I had 8 factorial, couldn't I write 8 factorial as 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8, right? I don't have to start with 8, do I? Okay, so it's okay to go backwards. So we ended up with n on that one. What should I end up with on this one? 2n. So this is really 1 times 2 times 3 times 4 times 5 2n. Whatever that might be. And then that would be your answer. You don't actually have an answer, it's just a weird looking answer, but you're telling me that you realize what you would end up with. If I gave you n, then we'd know where this would actually end up. So let's look at simplifying factorials, which are down below. So 8 factorial, and I'm going to give you a shortcut eventually, but not today. So 8 factorial will be 8, 7, 6, 5, 4, 3, 2, 1. Over, divided by 2 factorial, 2 times 1 times 6 factorial, 6, 5, 4, 3, 2, 1. Everything in your denominator should cancel out with your numerator. Can't I cancel this entire 6 factorial right here with 6, 5, 4, 3, 2, 1 up here? Right? And then doesn't this 2 cancel into the 8 4 times? And it doesn't matter that my 1 doesn't cancel out to 1, right? That doesn't matter. So I've got 4 times 7, which is what? So 28. You can also do it on your calculator. There might be times when I tell you have to show your work out by hand, right? Or that you could do it in the calculator. So if we did it in the calculator, so I'm going to take 8 factorial, and I'm going to divide it. I'll use parentheses. If I don't use parentheses, it's only going to divide by the 2 factorial. You'll end up multiplying by the 6 factorial, so make sure that you use your parentheses. Then we get 28. If you don't use a parentheses, you won't get 28. You get some bigger number, really big number. All right, so you try this one, and then we'll talk about C. So you're okay with that one? Okay, and if you want to check on your copy, you can. Just make sure that you use parentheses here and parentheses there. Does it work? Okay. So then this one we need to talk about. Now you could, okay, if we set up here that 2n factorial was 1 times 2 times 3 times 4 times 5 to n, right? Then you would be thinking, okay, up here I'm going to put 1 times 2 times 3 times 4 times 5 n, right? But what did I say about the denominator on both of these always had to happen? They always have to cancel out. Let's focus on the denominator first. So if we focus on the denominator first, wouldn't our denominator be like 1 times 2 times 3 times 4 n minus 1? Right? So that means that our numerator has to kind of look the same. 1 times 2 times 3 times 4 What term in the sequence is before n? N minus 1. One before it, we're going one backwards, right? One backwards would be n minus 1, wouldn't it? So wouldn't I do n minus 1 times, and then the next term would be n? Do you see where I'm coming from? I'm going to put real numbers in here so you can be assured that it does work. And so then doesn't all of this cancel with all of that? And aren't we left with just an n? So n factorial divided by n minus 1 factorial should give you just n. So what number do you want to let n be? Well, okay, let's choose something other than 1. 5. Okay. I think in my notes I chose 4. But it doesn't matter. So we're going to put 5 in here. And so if I let this be 5 factorial over, it would be 5 minus 1 factorial. Wouldn't this equal 5 times 4 times 3 times 2 times 1 up top, correct? And then 5 minus 1 is what? 4. So this would be 4 times 3 times 2 times 1. Doesn't all of this cancel with all of that, and aren't you left with just a 5? Did it work? Couldn't I have just said from the beginning, oh, this is one less than that, it's just 5? It worked, right? So you're going to have, and that's going to be a little frustrating for some of those questions on your homework because those are uncomfortable, but work with it. Then let's talk about, oh, I heard that. Some of, they're fun. Oh, okay, I can't either. So we'll be in the same boat. Whoops, let me back out here a little bit. So we're going to find the sum of sequences. And it's just shorthand notation to say that you've got, if you're looking at, if I just look at this, and let me closer in on here. If I look at this one, this is my lower bound. So on this one, I've got a 1, right? So my lowest number for I is 1. My highest number would be whatever this one is up here. It's saying n right now, but it's going to be a real number like 10. So you might have 10 items in the sequence. You'd have to figure out what each of those 10 items are and add them all together. The joy of this is you're going to be able to use your calculator in some form or fashion, but not for tonight's homework. Sorry. So let's just look at this, the sigma notation, and yes, I agree with you. I have a hard time with those little e thingies. Don't let that bother you, just make them look close enough. Okay? Alright, so for this one, I have a 1 for my lower parameter, and it goes up to 5. So I have 5 terms in the sequence, don't I? Sometimes this might be a 0 to 5. So if it's a 0 to 5, you have 6 terms in the sequence, right? Okay. So you're just going to find your all of your different terms and add them together. So I'm going to take 3 times 1, because that's my first one. Because this is 3i, this is your pattern. All I'm doing is plugging each one into 3i, plus 3 times 2, plus 3 times 3, plus 3 times, you might want to write it vertically because you can see I'm going to run out of room here shortly, plus 3 times 5, right? So I have 3 plus 6 plus 9 plus 12 plus 15. 3 and 6 is 9, 9 and 9 is 18, 12 and 15 is 27, right? And then I can finally add those together and get 30, 45 for a total sum. Now you can check it on the calculator. Are you ready? You still have to show the longhand math today, but you can check it on the calculator. So where do you think it's going to be, the segment notation? Yep, it's going to be under math. Oh, where did it go? No, I don't see it. Well, oh yeah, it might be there. There it is. Yeah, keep going. There we go. So there it is. Now, if you have an older calculator, yours is going to look a little different than mine, I think. See how mine has all the fun little boxes in it? Yours doesn't do that, does it? This is what Amber's looks like.
Yeah.
Okay, so Amber's, before she presses hers looks like this underneath the math button. Do you not have it at all? Oh, you unlucky ducks. Is solver maybe?
Maybe. I don't know.
Did you try that?
Yeah.
I don't know. I'd have to look at your older calculators to really figure it out. That's it? That's all our only choices? Huh. Here's what I would suggest, because I don't have the older one.
I just added it.
Yeah, you can just add them, but it's got to be on there. So Google it and see.
Okay.
And meanwhile, I'll Google it. I just don't have the older one. Because you're going to want it. Just trust me on this one. So those of you who are lucky enough to have the newer calculator, go yay. Because then I can put in my parameters, right? So put in your variable right there. We'll call it x. And then our x here, I and x, it doesn't matter, right? So I'm going to put in my lower parameter of 1. And then I'm going to scroll up and put in my high parameter of 5. And then over here, I'm going to put in my pattern, but I'm not putting in 3i, I'm putting in 3x. And then what do we get? 45. So it calculated it for you. So we'll Google for the older calculators and see. Nobody asked me that last year. Go figure. All right, so look at this one. So you're just doing the same thing, right? So let's do it vertically this time. So we've got 1 plus our k is 3 squared, which equals 1 plus 9, which is 10. And then 1 plus 4 squared, which is 1 plus 16, which is 17. 1 plus 5 squared, which is 1 plus 25, which is 26, and 1 plus 6 squared, 1 plus 36, which is 37. And then you want to add all those together. If you add them all together, we get 90. This one's a little different, isn't it? So we have a factorial in there. So we get 1 over 0 factorial, and we're going to go up to 8, right? This one gets fun. So we get, what's 0 factorial? So we have 1 over 1, which is 1. So there's one of them. And then 1 over 1 factorial, which is 1 over 1, which is 1, right? There's 2. And then we have 1 over 2 factorial, which is 1 over 2 times 1, which is 1/2. 1 over 3 factorial, which is equal to 1 over 3 times 2 times 1, which is 1 over 6. So I'm going to give you the rest of them. Let me show you my work here. Because we are running short on time, I want to show you the rest of them. So here's what I've done. So if you find all your factorials, you've got 1 over 1, 2, 6, 24, 1, 27, 28, 50, 40, and it gets really big, doesn't it? And if you add all those together in your calculator, it gives you approximately this. I believe if you try to add them as fractions, I want to say, if I recall, it wouldn't give me the actual fraction. I'd have to play with it. I can't remember. Don't pack up, we're not done. I hear you trying. Yeah, because this is what your calculator gives you. So it's really, oh, I forgot to put on here then, huh? Oh, weird. I'm going to have to double check that. Oh, they do 8 factorial, that's my problem.
You have to put an X in there, 8 is there.
Yeah, that's my problem. Anyway, I should have put an N, exactly. So take that, then look at this part. You should not be packing up. Are you in a hurry to go? We're not in a hurry to go. All right, so then we have an infinite series. It just means that there's no end to the series. Y'all don't care about that, do you?
35 will cover 90 today.
It's like, please look.
35 will cover back 90 today. Thank you.
Okay. So here's what's going to happen if you have an infinite series. You're going to break it into 2 parts. So if I have a lower parameter of 1 but an upper parameter of infinity, and my pattern is 3 over 10 to the I, okay? So that means I've got, if I start with 1, I'm going to just start with the first 3. You're going to start to see a pattern because there's not just 3 terms in the sequence. The directions here did say find a partial sum for the first 3. And so that's what I'm doing here. So I did 3 over 10 to the first. Isn't that 0.3? 3 over 10 squared, that's 3/100ths. Isn't that 0.03? 3 over 10 cubed, isn't that 0.003? And if I add these together, don't I get this? What fraction does that appear to look like? 1/3. And then if I continue on, and all I did was I continued on longer, I even went out to the 5th and to the 4th, and it does end up coming out to be 1/3. So try out to the first 3, do your homework, and come back with questions tomorrow.